And we decided to analyze
me here. So I will talk again about alpha on carbon-12 reaction, but this time we will use electrodisintegration and to show some calculation which we did and potential of this reaction in some future experiments. Okay, so let me just turn this off. Okay. So when you do modeling of stellar evolution, you have two big parts. One of them is how to handle transport of material inside the star, and another part is how to handle nucleosynthesis. So nucleosynthesis should be something easy, because it's just described by system of differential equations, and only thing you need to put in is a nuclear input which enters as reaction rates at gamma energies. But unfortunately for alpha plus carbon-12 gamma, the uncertainty on this rate is quite large. So what people do is they take some range of stars, mass of the stars, and they take some central value of this reaction rate and just calculate the evolution of a star for a certain range of this reaction rate. So if they go, for example, 3 sigmas above the central value, after helium burning stage, they end up with a core of a star which actually doesn't have almost any carbon inside. The carbon burning stage is skipped, and the star goes directly into oxygen burning stage. On the other side, if you go just 3 sigmas below your central value, you end up with a lot of carbon in after the helium burning stage, and you have carbon burning stage, and your star lives much longer. So, and if you look at some, let's say mass, for example, 75 solar masses, and you look at all your ranges of your alpha plus carbon-12 rate, you end up with quite different scenarios at the end, and this is the map of this ending of scenarios. So that's from one of the newest calculations from Farmer. So they actually used LIGO and Virgo gravitational wave data from binary black hole mergers, and tried to use this to determine the alpha plus carbon rate, and here in green are their results depending on different observations. Of course, there are other astrophysical observation approaches. One of them is galactic chemical enrichment model, so almost 30 years old data and observation of white dwarfs. And we are here interested in the nuclear approach. Okay, why is this so complicated? So cross-section is of course very small, so it would be very difficult to measure at gamma energy the rate. Also the cross-section is also a little bit complicated. It has two dominant components, E1 and E2, which also have their own substructure, of course. So what people do is actually measure as close as possible and then extrapolate to gamma energy. And of course, when you go down in energy, your error bars just go up. So the idea is to improve in this region below 2 MeV the data. So, and the accuracy of the data. So there are several possibilities to do this. So direct reaction, so either you shoot alpha beam on carbon-12 and measure the angular distribution of your gammas. You can use a carbon beam and detect recoils. You can use indirect reaction, so beta decay of nitrogen-16, or you can use inverse reaction. So you can use either photo disintegration of oxygen-16. So there is a bubble chamber experiment, and from previous talk, time projection chamber experiment, and here is, I also plotted their nice result from last year. And of course, I will talk here about electrodisintegration of oxygen-16. So in photo disintegration, you induce disintegration with real gammas. In electrodisintegration, you induce disintegration with virtual gammas. And we already published a paper together with William Donnelly and Richard Milner 3 years ago, where we developed some model how to go from the electrodisintegration to direct reaction and back and forth. And I would also like to say there is also a PhD thesis of Stefan Luckenheimer. So part of his thesis he devoted to the electrodisintegration of oxygen-16 and what they are planning to do in mines within MAGIC's collaboration with the new MESA accelerator. Okay, so there have been some experiments before with electrodisintegration. So almost 21 years ago, that was at NICEF, but they were not interested in this astrophysical part. They were like measuring alpha knockout from oxygen-16, but in 2000, Enjat Sentalovic proposed an experiment at MIT Bates and at their storage ring, but at the end they lost funding and nothing happened there at Bates after this proposal. And William Donnelly also talked about this at one conference, which was actually in Pula in Croatia. So, and then nothing really happened on this side. So why now? So first, and what is advantage here? So compared to the direct reaction, it is inverse reaction. In this particular case, it has a larger cross section than direct reaction. But now we have new generation of energy recovery linear accelerators, which have electron beams around 10 microamps or larger. And people already start, we have gas jet targets, and together you get a really high luminosity, which you need to measure these low cross sections. Okay, so what is happening in this reaction? Electron scatters, exchanges a virtual photon, and it dissociates your oxygen-16 target, and you measure scattered electron in coincidence with produced alpha particle. So that's the idea. So energy recovery Linux are not a new idea. They were proposed in Novocimento. I think it's called like this. The paper in '65. Essentially, idea is you inject electron beam into your linear accelerator. You do something with it, and you return it back into same accelerator, but out of phase. So now your beam is giving energy to the cavities, and you dumped out the same energy beam which you injected in, so you recover energy. So one of such accelerator have been built at Cornell. It is called C-beta. So it's capable to delivering beams between 42 to 150 MeVs at 40 milliamps, and it is actually demonstrational ERL for, and will be used for cooling the ion beams at electron-ion collider, which will be built at BNL. So there is also MESA in Mainz. I think they already built the building, and soon they will start to assemble the accelerator. So we are, for our purposes, we are interested in ERL mode, where this accelerator will deliver a beam of 105 MeV. First, they will start with 1 milliamp and then upgrade to 10 milliamps. So here is the magic setup where this will be measured. So I gave a talk earlier this year at Triumph, and it was some so new possibilities with Ariel facility. So at the moment, Ariel only has this part here, so only LINAC, and at the moment it's only 10 milliamps at 30 MeV. But they will upgrade to 50, and there is a possibility to build an loop, and you have energy recovery LINAC. So there's also possibility to use this when it will be built. Okay, now you need also a target. So you want to measure at energies below 2 MeV. So your produced alpha will have low kinetic energy, so you have to have a target without windows. Essentially, you need a jet of gas, and Magic's collaboration already built such target, and we're running it, started to run 2017 up to 2020. 20 in the just before COVID exploded, but we were using it with hydrogen gas. So for our purposes, we will exchange it for oxygen 16. Okay, so this is how it looks in the scattering chamber. So beam goes from the right to the left. Oops, to the left. Here is a nozzle, and a jet goes out, and you catch it here with this catcher, which is attached to, on the other side, to big pumps. So you want to have a jet, shoot a beam through it, and take it out immediately, so you don't have gas around. And here is installed in A1 3 spectrometer facility at MAMI Accelerator in Mainz. Okay, so that's from Stefan's PhD. So they were planning to have 3 phases. Phase 0 should be in A1 collaboration hall, and the idea was to test silicon strip detectors, how they perform in this very hostile environment with scattered electrons, X-ray, and all other stuff. So how well you can measure alphas with those detectors in this environment. Phase 1 and 2 would then be in a new MESA building with new accelerator. Unfortunately, COVID happened and they didn't do anything for phase 0. So we need to wait. And they plan to do something with oxygen 16 at the end of this decade in early 30s or something like this. So unfortunately, we need to wait to have something from them. And one interesting thing for phase 2, they would like to build a 0-degree Tiger, and because there you have the highest rate of your scattering electrons. Okay, now everything would be nice if oxygen-16 had only one isotope, but there are also two other isotopes, and they will also. So here is a nice plot for photonuclear dissociation. So even if you deplete the oxygen 17 and 18 by factor of 1,000, you will still have alphas from which cause a background in your region of interest. Also, you will have some problems from nitrogen and dissociation, so from protons. So if this happens in photo disintegration, it also happens in electron disintegration. Now, how can we solve this problem? So I looked at the alphas which are produced at in this range from 1 to 1.1 MeV in center of mass energy, and I ran these alphas for all this and proton from these reactions through SRIM simulation, and I wanted to see what would be the energy spread if my particles go to 2 millimeter wide oxygen jet. How this jet disturbs these particles, and if you look at the kinetic energy, so alphas from oxygen 16 and 17 are very well separated due to different Q value of the reaction, but protons overlap with alphas from oxygen 16. Now you can solve this by measuring time of flight. Essentially, you would start measuring time when you detect the scattered electron and stop when you detect an ion, and then you can use this time of flight to separate the protons, and you would get very nice clean signal for the alphas which you want. Now I also looked what is happening in the angular spread using SRIM simulation when your alpha particles go through the oxygen jet. So of course, if you go lower in the kinetic energy, the spread increases. Now the virtual photon advantage comes in place. So if you in the real photons, for real photons, the transferred energy is equal to a transferred momentum. But in the virtual photon case, you can fix the transferred energy, and you can increase the transferred momentum. So you can do this by either raising your beam energy, or you put your spectrometer to a larger electron scattering angle, and in this way you can increase the kinetic energy of your produced alpha particles and move away to better angular spread. And you can use this fact only for the alphas which are produced in direction of the virtual photon and a little bit around it. So the idea is to put your ion detectors in direction around the direction of the virtual photon for a particular kinematics. Okay. So if we lay out an ideal experiment for which I did calculations in publication is PRC. So you would have an electron spectrometer and some ion detectors in direction around the direction of the virtual photon. And in that particular case, I choose to have like the angular coverage for on the one and other both sides of 60 degrees. And I calculated for 40 MeV and these energies of the C beta accelerator. That was published in that paper, but for talk at the REL and for here, I decreased the beam current to 10 amps, and I chose this energy from the REL and the 114 from the C beta. Now, if you go low in beam energy, then this angle between the virtual photon direction and the beam direction decreases. So it decreases so much that you cannot take the full 60 degrees on the right side. So I only taking into account this like a half of this cup of detectors, so as an acceptance. So I can easily compare results which I get from these three energies. Okay, now if you have a situation when you have unpolarized electron beam and unpolarized target, then your cross-section formula looks like this. And most important here are these response functions. You have longitudinal, transverse, and two interference response functions. And for the direct reaction, you only have the transverse response function. Now, when you go into real photon limit, these two transverse response functions are equal, and that's the way to go from back and forth from electron disintegration to direct reaction. So you need to go to a real photon limit in the electron disintegration, and then you can interchange these two. Okay. Now, of course, you need to calculate the multiples. So on the right side, there is an RT response function which should be familiar from the direct reactions. You only have electric response, and in a longitudinal you have Coulomb response. And into this interference LT term, you have both of them. Okay. Now, after you calculate the multiples for all these responses, then you also have to somehow model your matrix elements. So we choose this parametrization here because when you take a long wavelength limit and continuity equation, you can relate the leading order coefficients A prime E and A prime C. So we choose this particular parametrization. So we have disentangled A prime, so the leading order coefficients, which is only dependent which depends on energy, and B prime next to leading order coefficients, which depends on the three momentum transfer. So, but this was done so you can easily go at any Q value. You can easily go from the direct reaction to to electron integration, but this needs to be verified experimentally if such parametrization works. Okay, so we fixed A prime by choosing all the data below 1.7 MeV, and just we fitted a second order polynomial. We didn't like use some fancy R matrix fit or something similar, because we just wanted to focus on this this region And we wanted that it's really governed by the data measured in this region. Okay, this was used to fix the leading order coefficients. Unfortunately, we don't know anything about the next to leading order coefficients. So here we needed to do assumptions. So we assumed that they are of strength 1, and we chose sign plus. So we also don't have any knowledge about C0 multiple. So we also choose that it's strength 1 and sign plus. For the PRC paper, we modeled 2 cases. Either it's equal, A prime C0 is equal to A prime E2, and the case B where it's when we decrease the strength by half. But for these calculations, I will show you only results for case A. Actually doesn't affect the statistical error estimates of your results for SC1 and SC2. But in real experiments, we will need to fit on this. So, and determine it from a real experiment. And since we are below 1.7, in this phase, shifts only Coulomb phases contributes. The part from the elastic phases are close to 0. So for calculations, we neglected this part. So we took only Coulomb phases. Okay, now your formula is actually fully determined, and all you need to do is Monte Carlo integration of your cross sections for your beams of choice. You get the cross section, you multiply this with integrated luminosity, and here are some examples what you expect after 100 days of measurement for these parameters. So in the beam from 0.9 up to 1 MeV, it's these numbers. For the beam from 1.3 to 1.4, numbers are much larger. You have now here number of events which you expect, and you convert this into statistical errors, and you go all the way back to SE1 and SE2. So essentially, you fit your cross-section formula with 3 parameters, and now you get them with statistical uncertainty, and then you recalculate this into SE1, SE2, and of course you also get this non-astrophysical factor because your model demands it. Okay, and now how it looks with the data. So you can clearly see that you get nice improvement in terms of statistical uncertainty. So compared to the data, so this way should at least in terms of statistical uncertainties improve the data. And if you look now, I just recalculate everything into relative statistical uncertainties and plotted the data for the these energies 50 and 30 MeV. So as you can see, the best thing is to measure with the highest beam energy. Now, why I choose also 30 and 50? So this with this energy, you are at lower Q transfer, and you are closer to real photon limit. So if the parametrization of these matrices don't work as we written there, so we cannot disentangle the energy dependence of the leading order coefficient from the Q dependence. Then you actually need to also know the Q dependence of your results to be able to extrapolate to real photon limit. So if this parameterization doesn't work, this 30 MeV and 50 MeV accelerator suddenly starts to be very interesting site to also measure this reaction. Okay, so let me summarize or conclude. So we developed a model, and we used possibilities of new energy recovery LINAC accelerators and the J target, and use calculations to estimate the S factors for alpha plus carbon reaction, and we saw that we can really improve the statistical precision in this region of interest. Now, in the direct reaction experiments, I mean, people, when they measure this reaction, they measure with one beam energy and then collect the data, then move a different beam energy and measure the data. Now, because your electron accelerator, electron spectrometer has a certain acceptance in momentum of your scattered electron, essentially, at once you can measure the whole range of center of mass energy. So here is just estimation. If you use, for example, 114 MeV and 10% of acceptance of your spectrometer, you can measure from 0 to 10.5 MeV in this center of mass energy in just one run. You just collect the data. Okay, what is actually, where to go from now? We need some shorter run at higher center of mass energy to test everything. I gave here a lot of assumptions, and you need to test this. And the only thing you need is an experiment, of course. And for more details, you can also read in these publications of mine and my colleagues. Thank you very much.
So, first time for a discussion, please.
So it looks like the statistical uncertainty is going to be very competitive. Do you have an idea of how big the systematic errors are going to be, even after you do all these coefficients?
No. We did. I show you just some systematical consideration, but I didn't do any analysis with the what's the name, with the systematics. I know that also, like Moshe said, they have problems with the beam spread. You will also have problems with electron beam energy spread. But here, since you measure the 4 vectors of both the alpha and the scattered electron, your system is actually overdetermined. You can actually ask yourself, what was the beam energy which produced these pairs? And you can recalculate back the beam energy and maybe correct it. So you can do this. So, but there will be some. I mean, we didn't run what's the name, the detectors inside the scattering chamber, and it's the question how all this background will affect the detector. So this is uncertain. So, and you really can know this when you put it in and shoot the beam.
Yeah. Okay. So we have a question from remote, I think. I see I lifted the hand by Moshe Guy, is that?
Yeah.
Moshe, can you hear?
Yes.
Well, I think you lifted your hand for a question, maybe?
I have a question, yes.
Yes, please go ahead.
So in the virtual photon flux that you're producing, do you have the same sensitivity for E1 and E2. I thought that your experiment will be mainly sensitive to E2. Is that correct?
No, it will be sensitive for both. It will be sensitive. Yes.
With the same sensitivity?
I think so, yeah.
Okay, thank you.
I had also a question. Could you like your slide number 30?
This one.
These are, I didn't plan, so this is the relative uncertainty of SE1
Yes.
as a function of the energy. And previous experiment, what do you mean for previous experiment? So directly experiment.
I didn't direct.
So
Yeah.
carbon 12 propaganda.
Yes.
Because
Yes.
it looks a bit. And this is in percent.
Yeah, that's in percent.
Okay. And for the two, and just one question. I'm not really the question was also with the EE primes, so electron scattering. Isn't it possible to populate states that you don't populate
Yes.
carbon 12 propaganda reaction?
Yes, of course.
In carbon 12 propaganda, you only populate states with natural parity. And while I think in principle, I'm not really an expert on that, but I guess you don't have a constraint, and you should also take care of that you could populate states that you do not populate over the horizontal.
In electron production experiment, usually, I mean, you need to measure both scattered electron and produced alpha particle. So you can then reconstruct the missing mass. Missing mass is here the carbon. You need to calculate essentially from this energy and momentum balance. You need to select events where carbon is in ground state. So you can determine that you are selecting. You need to cut on the events where carbon is in ground state, and you are fine then. So, but of course you can also populate other states. You populate everything, but you can determine this, that you are cutting on events which you are actually contributing to this.
What's your expected count rate in the electron spectrometer? What's your expected count rate in the electron spectrometer with such a huge
I
current?
didn't calculate this.
Yeah, I'm just wondering what influence that has on, because you're using that as a tack with time of flight. If it's too high, then it's going to be tough.
Yeah, of course, if you are very close to the on the low scattering angle, then it will be you will have very high rate there. So I mean, we did measurement with the on hydrogen, and you need to lower the elastic scattering, and when you are at very low angles, you need to lower the beam current, because it's just thunder in your detectors.
Can I have a question? So can you come back to there was a slide where there were two spectra with showing counts at two different energies.
This one.
Yeah, this one.
Yeah.
So why such a huge difference in terms of number of events?
This one was cut at center of mass energy between 0.9 and 1 MeV, and this one is at 0.3, between 0.3 and 0.4. So it's just the cross section falls.
Yeah, I mean, it's just because they are very close anyway.
Yeah.
So I was impressed because it's just almost an order of magnitude less.
Of course.
So what?
So this is why it's so difficult.
Sure. But probably is simpler, so is easier than the gamma beam. So the gamma.
I think gamma is already at the moment happening, so they will have their results, and we will start to. I mean, I think mines will be the first to do something there, but it will be like in 10 years or so.
But which one is the most selective? So coming back to your question, So the electron or the gamma in terms of selectivity, trying to be similar to approach to the real reaction.
But I mean, it's the same. The both are the same. It's disintegration, and in photo disintegration, you just use real photons, and here you use virtual photons. So the cross section is, of course, with virtual photons complicated, much more complicated, because virtual photons can be also polarized in the longitudinal direction. Real are only transverse.
Okay.
So yeah.
Nice. Nice.
Okay.
Thank you.
More question? Oh, okay, so then.
Okay. Thank you.